Welcome. Now we will discuss heat transfer from extended surfaces, that is fin. Objective of this presentation are to discuss temperature distribution along the fin, to discuss heat transfer by fin, and to discuss efficiency and effectiveness of the fin. First is introduction. Heat transfer by convection from the extended surfaces or from any surfaces is given by Q equal to HA T naught minus T infinity, where Q is the heat transfer by convection in watt, H is the convective heat transfer coefficient in watt per meter square per Kelvin, A is the surface area of extended surface or the base surface, and T naught is the base temperature or wall temperature minus fluid temperature T infinity. Heat transfer by convection depends upon convective heat transfer coefficient, surface area, wall temperature, and fluid temperature. For given convective heat transfer coefficient and temperature difference, the option for increasing heat transfer is only by increasing surface area A. Hence, in order to increase surface area, extended surfaces of different shapes are attached to the base surface to increase area, and which increases heat transfer rate for fixed heat transfer coefficient or for smaller heat transfer coefficient, and for fixed temperature difference. Extended surfaces increases surface area and increases heat transfer. So fins are very useful when the heat transfer coefficient is smaller. There are wide variety of application of fins. Fins are used in air-cooled engine to cool the cylinder, and the circumferential fins are used in engine. Then fins are also used in electronic devices to dissipate heat generated in the chips or electronic device. Fins are used on a electric motor casing, which are longitudinal to dissipate heat from the motor. Fins are used on the cylinder of compressor and also used in intercooler and aftercooler of compressor. Fins are also used in the absorber tube of solar flat plate collector to increase heat transfer rate from that to the fluid from the solar energy. Fins are also used in computers to dissipate heats produced in chips. Now we'll discuss types of fins. The various shapes of fins are used depend upon their suitability. Circular circumferential fins are used in an engine to cool the engine cylinder, and also used on the compressor cylinder, while longitudinal fins are used in an electric motor to dissipate heat from the electric motor outer casing. On this slide, we have some typical shapes of fins. First is the uniform straight fin. We have this is the base area over which this rectangular fin is attached, having this length, then the width, and this is the thickness of fin, and the area to which this fin is attached is called as base area, and it is assumed that base area is having temperature equal to the other area of the base surface. And we have the second fin called as tapered straight fin. Then third is spline fins. Then fourth is annular fin, and last one is pin or pines, having different cross section areas. So it is like pins. That's why the name is pins. Pins are analyzed for temperature distribution and heat transfer rate. And in design of pins, these parameters are important. So in analysis of pins, some assumptions are made, and these assumptions are: the heat transfer is considered at steady state, and there is no heat generation within the pin. Then uniform heat transfer coefficient H over the entire surface of the pin is assumed. Then the material of pin is homogeneous, and isotropic means thermal conductivity of material is constant. Then contact thermal resistance between the pin material and the base material is negligible. Heat conduction one dimensional. Negligible radiation loss or heat transfer by radiation is negligible. Temperature distribution and heat flow through rectangular pins. Now we'll discuss. Here we have rectangular pin, and this is the base surface to which this rectangular pin of length L, width W, thickness T is attached, and it is in ambient air at temperature T infinity, and the convective heat transfer coefficient between the pin surface and ambient air is H. Then K is the thermal conductivity of the pin material, and usually pins are made up of high thermal conductivity material to have a effective application of pins. And typically the material used for pins are copper, aluminum, brass, and this base surface is at temperature T0, and surrounding temperature is T infinity, and AC is the cross section area of the pin. To determine temperature distribution and heat flow through rectangular pin, we will first obtain the general differential equation. For that, we will consider the element of thickness dx at length x and perimeter p, and the heat conducted in the element is qx. Heat conducted out is qx plus dx, and heat convected out is q convection from the element. And in obtaining equation, we will consider energy balance for this element, which is shown by the red color. Now we will first see the heat conducted in the element Qx, which is given by the Fourier's law, and it is minus Ka C dt by dx at x, and heat conducted out the element at x plus dx is qx plus dx equal to minus Kac dt by dx x plus dx, and heat dissipated by convection from the element q convection equal to heat transfer coefficient into surface area of pin, which is element, which is perimeter, into thickness of element into temperature of the element minus fluid temperature. So q convection equal to hp dx t minus t infinity. Now considering energy balance for the element of thickness dx at distance of x and having perimeter p, we have heat conducted in the element is qx, which is equal to heat conducted out the element plus heat convected from the element. So Qx equal to Qx plus dx plus Q convection. By using Taylor series expansion, Qx plus dx equal to minus Kac dt by dx x plus dx equal to minus Kac dt by dx minus Kac d square t by dx square into dx minus so on. Substituting the expression for different terms in energy balance equation, we have Qx is given by this one and Qx plus dx is given by this term by eliminating higher terms and plus heat transfer by convection. Now in this equation, K minus Kac dt by dx at x from both sides will get cancelled. Then remaining we have is Kac d square t by dx square dx equal to hp dx t minus t infinity. Now transferring Kac to this side and cancelling dx and further rearranging, we have d square t upon dx square minus hp upon Kac t minus t infinity equal to 0. Now putting hp upon Kac equal to m square is one parameter which is combination of h, p, k, a. So equation becomes d square t upon dx square minus m square t minus t infinity equal to 0, where m equal to root of hp upon Kac. M is constant for a given field if H convective heat transfer coefficient and K thermal conductivity of material of fin are constant. By transforming the dependent variable temperature T to excess temperature theta, we have theta equal to T minus T infinity. So the second order differential equation take the form d square theta by dx square minus m square theta equal to 0. And the above equation is second order differential equation having general solution equal to theta equal to c1 e raised to mx plus c2 e raised to minus mx, where c1 and c2 are constants and evaluated from boundary conditions, and m is equal to root of hp upon ka. And to obtain the temperature distribution and heat transfer rate, we will consider three cases. The case 1 is infinitely long fin, such that the tip temperature of fin is equal to surrounding temperature. Then second is short fin with insulated tip and there is no heat transfer from the tip, and the short fin with convection at the tip. So first is the long fin, infinitely long fin. So this is the infinitely long fin which is attached to this space at x equal to 0, and the length of fin L is equal to infinity, and heat from the base will conducted into the fin along the length, and it go on decreasing from base temperature to surrounding temperature. So in infinitely long fin, temperature of tip is become equal to surrounding temperature, and this is the typical temperature profile for infinitely long fin. This is the second fin, short fin with convection, short fin with insulated tip. So there is no heat transfer from the tip, means Q is 0 and Q is given by Fourier's law minus K dt by dx equal to 0. So K and A are not 0, so dt by dx is 0 is the boundary condition for the short fin with insulated tip. So figure 2 shows the short fin with insulated tip and temperature distribution from base of the fin to the tip of the fin. Here at the tip, temperature of fin is higher than the surrounding temperature. Figure 3 is for the short fin with convection at the tip. So heat conducted at the tip is convected to the surrounding, and the temperature distribution in this case is like this. Now we'll see the heat distribution equation and heat transfer equation for infinitely long fin. When fin is long such that tip is at ambient temperature, then we have boundary conditions. X equal to 0 means at base temperature is T naught, that is base temperature, means x equal to 0, theta is equal to T naught minus T infinity, which is theta 0. This is the boundary condition A for infinitely long fin. Second boundary condition, when x equal to infinity, means length of fin is infinite, then T is equal to surrounding temperature T infinity, x equal to infinity, not L, and then theta equal to 0. Using boundary condition A, we have general equation is theta equal to C1 e raised to mx plus C2 e raised to minus mx. So for boundary condition A, x equal to 0, so e raised to 0, e raised to 0, 1. So we have theta is equal to C1 plus C2, and theta is equal to theta naught. So theta naught is equal to C1 plus C2 from the boundary condition A. Now using boundary condition B, x equal to infinity, and theta equal to 0, and again this term is 0, so C1 e raised to m infinity plus 0. So C1, this implies C1 equal to 0. So theta naught from this equation, now C1 is 0, so theta naught is equal to C2. So in a general equation, theta equal to C1 e raised to mx plus C2 e raised to minus mx. C1 is 0 and C2 is theta naught. So we have only second term, theta equal to theta naught e raised to minus mx. Rearranging theta upon theta naught equal to e raised to minus mx. Theta is t minus t infinity, theta naught is t naught minus t infinity, which is equal to e raised to minus mx. So this gives temperature distribution, and m is a parameter which is equal to root of hp upon ka, and x is the fin length, and the equation gives temperature distribution for infinitely long fin. Now we'll see the heat transfer from the infinitely long fin. So the rate of heat conducted at the base of the fin, Q is equal to minus KAC dt by dx at x equal to 0 according to Fourier's law. Now dt by dx at x equal to 0 we will obtain from the temperature distribution equation. So differentiating temperature dt by dx, we have e raised to minus mx as it is into derivative of minus mx is minus m into this constant to minus t infinity, and x equal to 0. So by simplification we have minus m t naught minus t infinity. By further simplifying we get the equation of heat transfer rate, Q equal to root of hp kac t naught minus t infinity. where T naught minus T infinity is theta naught. So heat transfer Q equal to root of HP KAC theta naught. Now we'll see the temperature distribution and heat transfer rate for short fin with insulated tip. For insulated tip, there is no heat transfer from the tip. Means we have adiabatic condition at the tip, and from the Fourier's law, Q equal to minus K dt by dx equal to 0. So at the tip, we have boundary condition x equal to L equal to dt by dx equal to 0. So x equal to L d theta by dx equal to 0. And at the base, x equal to 0, base temperature is Q naught. X equal to 0, theta equal to theta naught. So first boundary condition for the short fin with insulated tip is same as that of infinitely long fin. Only in second boundary condition at x equal to E, x equal to L, there is no heat transfer. So dt by dx equal to 0, which is adiabatic boundary condition. So by simplifying and solving using boundary conditions and determining constant C1, C2 in general solutions of second order of differential equation, we have temperature distribution for short fin with insulated tip, which is given by this equation, that is theta upon theta naught equal to T minus T infinity upon T naught minus T infinity, which is equal to cos of hyperbolic m L minus x upon cos of hyperbolic ml. So in short fin with insulated tip and short fin with convection at the tip, we will not discuss the detailed derivation of temperature distribution and heat transfer, but we will directly see the boundary condition and temperature distribution and heat transfer for the short fin with insulated tip and convection at the tip. So this is the equation which gives temperature distribution for short fin with insulated tip. Similarly, we have heat transfer rate for the short fin with insulated tip determined by the previous method using infinitely long fin, root of HPKAC T naught minus T infinity tan of hyperbolic ml. So in this case, tan of hyperbolic ml is extra term multiplier to the previous heat transfer rate. T naught minus T infinity is theta naught. So Q equal to finally root of HPKAC theta naught tan of HML, which gives heat transfer rate for a short fin with insulated tip. Now short fin with convection at the tip, we have boundary condition at the base x equal to 0, t equal to t0, x equal to 0, theta equal to theta naught, and at the tip of the fin convection is there at x equal to L. The heat conducted at the tip minus K C dt by dx given by Fourier's law of conduction equal to convection, which is given by Newton's law of cooling H A T minus T infinity. So x equal to L. By simplification, we have minus K d theta by dx equal to H theta. So further simplifying, we have d theta by dx equal to minus H theta by K. Temperature distribution for short fin with convection at the tip is equal to theta upon theta naught equal to T minus T infinity upon T0 minus T infinity, which is equal to cos of hyperbolic m L minus x plus h upon mk sine of hyperbolic m L minus x upon cos of hyperbolic ml plus h upon mk into sine of hyperbolic ml. So this gives the temperature distribution for the fin with convection at the tip and the next expression gives the heat transfer rate for the short fin with convection at the tip. Q equal to root of Hp KAC T naught minus T infinity tan of H ml plus H upon Mk 1 plus H upon Mk tan of H ml. Now we'll discuss efficiency and effectiveness of fin. This parameter gives performance of fin, whether fin is effective or not, or how much it is effective. First we'll see efficiency, which is simply ratio of actual heat transfer by the fin to maximum possible heat transfer by the fin if the entire fin area were maintained at base temperature. Mathematically, efficiency is equal to ratio of actual heat transfer rate Q to maximum possible heat transfer if entire fin were maintained at base temperature equal to Q max. For infinitely long fin, actual heat transfer is given by root of HPKAC theta naught, and maximum heat transfer from the fin is possible when the complete area is maintained at base temperature. So perimeter of the fin into length gives the complete surface area of fin into H into theta naught gives the heat transfer which is maximum possible, and after simplification, cancelling HP from numerator and denominator, we have root of KAC upon HP into 1 by L, and HP upon Ka is M. So 1 by ml is efficiency for infinitely long fin. So efficiency of fin increases with increase in thermal conductivity, increase in cross-section area, decrease in H, decrease in perimeter, and decrease in length. For short fin with insulated tip, efficiency is given by actual heat transfer to maximum. Actual heat transfer in insulated tip is root of HPKAC theta naught tan of H ml upon HPL theta naught. By simplifying, we have efficiency for the short fin with insulated tip equal to tan of hyperbolic ml upon ml. The next term is effectiveness of fin. It is simply ratio of the fin heat transfer rate to the heat transfer rate that would exist without the fin. So effectiveness is ratio of Q with fin to Q without fin. And putting expression with fin and without fin, we have effectiveness equal to root of Pk upon HAC. So effectiveness is directly proportional to thermal conductivity, perimeter, and inversely proportional to convective heat transfer coefficient and cross-section area of the fin. It is desirable to have effectiveness of a fin more than 1, then it can serve its purpose. Otherwise, there is no need to attach the fin or the base surface if the effectiveness is less than 1. And to have effectiveness more than 1, the fins are made up of copper, aluminum, brass having high thermal conductivity. So in this presentation we have discussed the type of fins, application of fin, then we have studied the general second order differential equation for a rectangular fin and its general solution. Then the general solution is solved for 3 cases: infinitely long fin, short fin with insulated tip, and short fin with convection at the tip. And in these three cases, we have studied the temperature distribution and heat transfer rate. Then we have studied the fin performance parameter, fin efficiency, and fin effectiveness. Thank you. If you have any doubt, mail me on sdbarate@kkwork.edu.in.